Hi, in this video I'd like to look at a couple of our cubic crystal systems. First of all, FCC, face-centered cubic, and then we'll look at BCC, body-centered cubic. All right? So let's start with face-centered cubic. So as the name implies, cubic, we're going to start with a cubic unit cell. And then in that unit cell, we're going to position some atoms. And so what we do with all the cubic unit cells is we position the atoms first at the corners, and then, as the name implies, in some other place, in the center of the faces in this case, and I'll show you that in a moment. So let's start off by putting some atoms on the corners. And I'm illustrating them here as little circles, but let me explain that a little bit more carefully and clarify something. So I've drawn a complete circle, but I should note that the atoms are modeled as hard spheres. Okay? And so if we have a hard sphere centered on the corner, that means actually some of that sphere is outside of our unit cell. And if it's outside the unit cell, we don't really care about it. So what I'm going to do is I'm just going to erase the portion of the circle or the sphere that's outside the unit cell. So it's going to look a little bit more like this. And I did that in those two steps to help underscore the fact that we're only concerned with the portion of the atom that's inside the unit cell. So what fraction of an atom do we have at each corner? Well, if we've sliced it this way, you may be able to see that we've actually got 1/8 of an atom at each corner. So then the next thing we'll do is we'll position the face-centered atoms. And so as the name implies, there's an atom at the dead center of each of the 6 faces. So we're going to put one here on the right side face, one on the very center of the top face, one on the center of the front face, and I'm going to dot in or dash in the ones on the back. So there's one on the back, one on the bottom, and one on the left side face. And so those face-centered atoms are circles right in the very center, so they're sliced in half. And so we're only interested in half of the sphere, or half of the atom. Half of the atom is inside the cube. So in fact, the next thing we could do is we could total up the number of atoms inside this unit cell. If there's 1/8 of an atom at each corner, and there's 8 corners on a cube, that's 1 complete atom contributed from the corners. And then how about the faces? Well, there's half an atom on each face, and there's 6 faces. 6 faces, that gives us 3 atoms contributed from the faces. So 3 atoms plus our 1 atom that we had over here gives us 4 atoms in an FCC unit cell. So that's a good number to keep in mind. And sometimes the notation that we use for that is n equals 4. So there's our FCC unit cell. We know where the atoms are and the fraction of an atom at each of those positions. So another thing that's useful to do is to calculate now the fraction of a volume that's occupied by atoms. So that equation is, and I'll illustrate over here, we call it the atomic packing factor. or you could call it the atomic packing fraction, I suppose, to underscore the fact that it's a fraction of a volume. It's the fraction of a volume occupied by atoms. And so the atomic packing fraction, or factor, we often just write as APF. And so, of course, the APF, the atomic packing fraction, is going to be the volume of atoms divided by the volume of the unit cell. And what will that be for FCC? Let's work it out. APF for FCC is going to be equal to, well, just the number of atoms inside a unit cell times the volume of a sphere, because again, we're modeling the atoms as hard spheres, divided by the volume of a cube, because we have a cubic unit cell. So n, the number of atoms in an FCC unit cell, is of course just 4. We work that out. 4 times the volume of a sphere, 4/3 pi r cubed. And then divide by the volume of a cube. Well, the volume of the cube is a cubed, where, of course, I'll remind you, the lattice parameter is a, and it's a cube, so all the edges are the same length. But this is not a good place to stop, because you've got a pesky r up in the numerator and a in the denominator. So it's not very much use to us right now. We'd love to be able to cancel those out. So how could we do that? Well, by expressing a in terms of r. So to do that, I can just stop for a moment, or step aside here for a moment in our derivation or our calculation, and draw one of the front faces of an FCC unit cell. So the front face of an FCC unit cell, I'll try my best to sketch it here, would look something like this. Okay? So the atoms are meant to be touching this central atom. And actually, that just reminds me, I didn't mention over here when we were looking at the unit cell, the direction of contact between atoms, because in my sketch, and I apologize for this, in my sketch it's not actually immediately obvious which way the atoms are touching. I drew the atoms as smaller circles, whereas I told you that I modeled them as hard spheres. So really, I was a little inconsistent here, and I apologize. If these were actually hard spheres, they would be touching across the face diagonals. So I'm just drawing some lines here with the red chalk to show the direction that the atoms are touching. You can see that over here in this two-dimensional sketch that I did. The atoms are touching across these face diagonals. If they were actually, the spheres were inflated, if you will, to the point where they just start touching, well, what would happen is the face-centered atom would just touch the corners. So I'm going to write that in over here for you. Atoms touch along face diagonals. Okay? So now over here we have our two-dimensional sketch. We've got A, and then this distance right here across the face diagonal, you can clearly see now in terms of the atomic radius, because we've got one radius, two radii here in the middle, and then one in the corner. So we could use Pythagoras here to work out a relationship between A and R. So A squared plus A squared equals 4R all squared, or 2A squared equals 16R squared, or A equals 2 root 2R. And I'll put a little box around that because that's an important equation to remember. And that's the relationship between A and R for FCC. So then if I take this result for A in terms of R and substitute back into our atomic packing fraction calculation, we'll be able to cancel out those irritating R's and A's. Oops. All right, so if I didn't make any mistakes, this should be where we are now. And you can clearly see that we're going to be able to cancel out the R's. And if you do a little massaging on this number and work it out, and I'll leave you guys to do that on your own, you come up with the atomic packing factor, which is 0.74. So that tells us that 74% of a volume can be occupied by atoms. No more than that, in fact. An interesting result, or an interesting point, is that 0.74 is actually what we call closest packed. So you could devote the rest of your lives to packing balls into a box and never, as long as the balls are the same diameter, never get more than 74% of the volume packed with spheres. A great question that students sometimes have is, well, wait a second, what if I went to tiny, tiny little particles? What if I took sand or flour, tiny little spheres? Intuitively, you might think at first, well, that's going to give us a larger fraction, isn't it? If I filled a box with tiny little spheres as opposed to big ones, shouldn't I fill more of the volume? And the answer is no. And how do you know that? Because we canceled out the radii. The atomic packing fraction is independent of the radius. As long as you've got spheres of the same diameter, you'll only be able to fit 74% of the, or fill 74% of the volume with spheres. So the last thing I can talk about with FCC is the coordination number. And I'm going to have to clear a little bit of board space to do that. So perhaps what I'll do is I'll just redraw my unit cell here, and I'm going to show you the coordination number, and I'll describe what that is as well. Okay, so I've got the face-centered cubic unit cell drawn again. And what I want to show you now is the coordination number. So the coordination number is the number, another way you may have heard it, is the number of nearest neighbor atoms. And so for metals, we could just pick any one of these atoms and count the number of atoms that's touching that particular atom. So for example, in 2 dimensions, the coordination number would be 4, because this face-centered atom is touching 1, 2, 3, 4 other atoms. But of course, we're in 3 dimensions, so it's going to be a little bit more complicated than that. I'm just going to erase that to give myself some room. So I find that the easiest atom to start with is this right side face-centered atom. So we're going to see how many atoms are touching that right side face-centered atom. Well, you know from this figure over here that on each of the faces, the central atom touches the four corners. So we would have this atom here, 1, this atom 2, this one 3, and this one 4. The next thing that's not so obvious from my sketch is that, in fact, these face-centered atoms to the left are also touching this right side face-centered atom. The direction between this atom and this one is actually the same direction in the crystal as the face diagonal. So this atom also touches this atom to the left, this front face-centered atom. So that we could call 5 and the top 6, and then the one in the back 7, and the one on the bottom 8. But the story doesn't end there, because of course this atom here is shared between this unit cell we've drawn and another one that exists but I haven't yet drawn to the right. And so if I draw in the unit cell that also exists to the right, you'll realize that there's 4 more face-centered atoms on the top, on the front face, on the bottom face, and on the back face that are also touching this face-centered, right side face-centered atom in our unit cell. So that would give us atoms 9, 10, front 11, and bottom 12. So the coordination number, the conclusion here is the coordination number for FCC is 12. And that's a great place to stop right now. Thank you.